it's been recorded, really. So for all you know, it's my pleasure to introduce you today our speaker for our seminar series. So our speaker today is Yorgos Stratis. Yorgos is a PhD, a postdoc fellow on the Center for Spiral. Right, I would say that it's a bit of a different postdoc that we have. So his background is on physics. So he's a physicist, experimentalist physicist. He joined the center in this past summer, 2020, as part of the experiential AI program through the Rouge Institute, the campus that Northeastern has in Maine. So he's interested in topics related to machine learning and signal processing as they are applied to physics, to problems in physics. And in particular, we are doing some work on quantum physics, along with some colleagues also on the physics department at Northeastern. So today the talk will be around these topics and also to get to know a bit more Yorgos. So thanks, Yorgos, and the floor is yours.
Thank you, Pau. Thanks everyone for showing up to my talk, or at least those of you who decided to spend their noon this Friday noon with me. As Pau said, my name is Yorgos Stratis. You might see my name spelled like this, but this is how you pronounce it phonetically. It's a little bit confusing. But anyhow, I work with Professors Pau Closas and Denis Erdoğmuş here in Spiral. And as Pau pointed out, I joined in July, this past July, through the experiential AI program. My background is in physics, and I'm really interested to see how we can combine physics and machine learning. And until now, pretty much physics went its own way, but we start facing issues that I believe and many other people think that can be resolved through machine learning. Some of those problems tend to be big data sets. Other problems tend to be more, how do we deal with theoretical models? So today I'm going to try and show you some of the basic concepts in quantum physics without exposing you to the entire quantum mechanics realm. And I will try ideally to make some connections and try to see if there's a way we can connect it to machine learning and quantum physics. For starters, I would like to pose some questions that have been troubling physicists. And number one is, how do we simulate any many-body system? Real-life material like a piece of paper, your pen, anything, consists of an enormous amount of atoms. We are talking about 10 to the 23 atoms at the least, much more. So even though we might have a good understanding about the laws of physics governing the microscopic scale, whether that's Schrodinger equation or some other formulation. So even though we might have an exact way of writing a mathematical equation down of how the interaction plays out, we cannot make predictions for any microscopic object, for the majority of them. So we have a hard time connecting the microscopic laws of nature, even the macroscopic for that sense, to actual predictions. So this is a problem that it's at heart of physics. How do we simulate many-body systems? And to that, a relevant challenge is, and really important for in applied physics and engineering is, can I make a material with specific properties? Probably the holy grail of such an example is a room temperature superconductor. That's a material that has zero resistance, zero electrical resistance at ambient room temperature. Right now, there are materials that are superconductors, but either they have to be extremely cold, something at best 77 Kelvin, which is like minus 200 or so Celsius. Sorry, minus, yeah, I think I got it right. or we have to put that material in extreme pressure. So again, the question becomes, how do I make a material that has the properties I want? And lastly, most physicists strive to put diverse physical phenomena under the same theoretical umbrella, because ideally we'd like to have one way of explaining everything. Such an example is, how can you explain the transition from gas to liquid, let's say for water, with magnetism, having a material that is magnetic and non-magnetic? And surprisingly enough, there's one model, one theoretical framework, which you can put these two seemingly different phenomena under the same umbrella. To start with, you cannot talk about quantum physics without mentioning the Schrodinger equation. And Schrodinger essentially created a time-dependent equation where you have an operator H, which we refer to as a Hamiltonian. And that can be a matrix, a differential operator, an integral operator. It's an operator of whatever you want it to be. So H is acting on C, which is a wave function, what we refer to as a wave function. And that gives us a time derivative, essentially, of the wave function. In a sense, this looks like a complex heat equation. For a good chunk of the problems we're dealing with in physics, we don't really care about the time dependence, and we're happy with a time independent version of the Schrodinger equation. What that means is, once the Hamiltonian H operates on our wave function remains the same. It doesn't change over time, but we pick up a constant factor, which we refer to as the energy. The energy is a real number, and that's related with the actual energies that we can observe through experiments. So if you're going to get something from this entire talk, the point is the following. Most physicists start with an H, the Hamiltonian, and our goal is to find Psi or E or one or the other. So normally this is our starting point.
Excuse me, may I ask a question quickly? Could you give us a nation on the size of each these matrices? I mean, this is matrix and vectors. I know about En because it's a scale, but a scalar. How about the rest?
It's coming up later on, but it depends on your system. For example, for atomic systems, which I'm going to talk later, there are countably infinite number of E's. So H is infinite in a sense.
No, I want to know that if it's a square matrix, for example, is n by n, and the other one is n by 1. What the psi are vector?
Yes.
Okay.
Yes, these are vectors, but we could, yeah. Where I was going, yeah. So we also impose certain conditions on our wave functions, and the most basic condition we want is we want the norm of our wave function to be equal with 1. And since our wave function can be complex, we deal with complex conjugates. And the reason we do this is because we want to turn our wave function into a probability density function that will allow us to find expectation values through the traditional way we do expectation values using integrals and the probability function, probability density function. You might notice that I have written this integral in a bit of an awkward manner, but essentially the order matters. So that's something that goes a little bit above my theoretical knowledge, but the punchline is that you kind of have to write it in this order. Now, again, as I had pointed before, either our main goal is to determine this wave function, or we might want to just, without calculating the exact wave function, to find a computationally cheap way to calculate expectation values, such as the energy I was saying before, or you might be interested for a different operator. Yeah.
So a quick question, maybe it was
Mhm.
naive. So that equation looked like the eigenvalues, eigenvectors equation. Is it that, or
Yes.
I just thought? Okay.
That is completely right. I was actually going to mention it, but I forgot it. So
Okay.
this is an eigenvalue equation. And when H is a matrix, a good old matrix, you can solve it with all the linear algebra.
Okay.
However, yeah, there are situations like the neutral atoms where you deal when H is a differential operator, where your problem becomes a Sturm Liouville problem, and it's still an eigenvalue problem, but you deal with functions.
Okay, no, that's perfect. I just wanted to make sure that my observation was correct. So it is in the
Yep.
time dependent.
100%.
It's going to get reduced to eigenvalue, eigenvectors
Yes.
extraction. If H is an n by n scalar matrix. Otherwise, we have to have some advanced ways of extracting that. Okay, thank you.
Yeah, but the issue is that H can be an extremely big matrix. So that's part of the problem.
Yes,
How do you
it's part of the problem even in linear algebra. Yes.
Yes.
Thank you.
So I'm gonna start this discussion by roughly where quantum mechanics started and having to do with understanding the internal structure of atoms. So atoms consist of protons, neutrons, and electrons, with the protons and the neutrons residing in the nucleus. And the proton is a positively charged particle. The neutron has 0 charge. And the electron makes a cloud which is surrounding the nucleus, and that's a negatively charged particle. I'm gonna start with the simplest element on the periodic table, which is the hydrogen atom, which has 1 proton and 1 electron. The cartoon I'm currently showing is not correct at all when it comes to how we understand the hydrogen atom nowadays. However, it can motivate certain discussion. It allows us to illustrate some points. So don't take this cartoon as the reality. Just take from it the basic physical intuition, which is that you have pretty much a proton, which is positively charged particle, and an electron. And normally in many pictures, you see the electron orbiting around the proton at a given radius r. So since these 2 particles are oppositely charged, they experience an attraction. And that attraction depends on the separation r between the 2. Now, as I have said, in order to determine our problem, we have to specify our Hamiltonian. And going back to the eigenvalue problem that Professor Ostadabas referred to, our Hamiltonian consists of 2 terms. The first one, which has a derivative, the Laplacian. It's a second spatial derivative, and that has to do with the kinetic energy of the electron. And the second term has to do with the Coulomb attraction, the attraction between the proton and the proton and the electron that we were talking before. The good news is that once you write down this Hamiltonian, it has exact analytical solutions for the wave function and for the energy. My point here is not for you all to memorize these expressions, but just to drive my point that we can calculate exactly these 2 quantities. So it's like game over, we won, kinda. So our goal now is to go to the next element in the periodic table, which is helium. So helium has 2 electrons, 2 protons, and 2 neutrons. Like before, the electrons are being attracted to the nucleus. However, this time around, the 2 electrons repel each other. Since they are charged by the same amount. They're charged with the same kind of charge. And again, the repulsion depends on their separation. So how does the Hamiltonian, how does our operator change having this extra term? It's in the following way. Like before, we have these two terms which are relating, which have spatial derivatives. The attraction term of the electron with the nucleus. And the last term is the repulsion between the two electrons. Unfortunately, even though we just have one term, this ruins the whole analysis, and we cannot find neither for the wave function nor for the energy analytical solutions. So one might think, okay, that might be a bit of an aberration. What about the other elements on the periodic table? Well, you can generalize all these atomic systems, essentially follow a certain formula to identify the Hamiltonian. So essentially the Hamiltonian has a structure in it. It consists of the spatial derivative, which is which has the same number as the number of electrons in our system, the attraction to the nucleus between the electrons and the protons, and the repulsion between the electrons. So right now I'm trying to show here is that in a sense, that kind of resembles a neural network with a specific structure, because every time we change the element we are looking at, the only thing we change is the number of electrons and the number of protons participating. But overall, it has a certain structure that just replicates itself. And the bad news is that the last 100 years, we were able to solve this problem, but we do not have a general way of approaching these solutions. So in a sense, we found approximations that apply for certain families of chemical elements, but we don't have a good way of connecting the two. So essentially, we have models that are specific to the system, and then we have to apply a different approximation. And this can be seen by just looking at the ground state energy of an atomic element. Here on the x-axis, I show the atomic number, Z, and this Z indicates the position of the element we're looking at the periodic table. So for example, Z equals 2 is helium, Z equals 6 is carbon. And here on the ground state, on the y-axis, that's the lowest energy. That's E1 we can achieve for each element. And one would think that we might have some kind of way of feeding energy as a function of the atomic number Z. But as we can see in this picture, this function is really jagged. It's not continuous in any, it's not well behaved. So we cannot essentially calculate the energy for a couple elements and then extrapolate for the next. It's a bit of a complicated problem.
May I ask a question?
Yep.
I think I missed that. This ground state energy, is it a steady state, a stable state of the atoms?
Yes.
Okay. And so what are the other states? So you can change the energy of an atom? I didn't know that actually. So these are the way that they are usually. Oh yeah, go ahead. Just explain a little bit that, if it's possible.
Yeah, well,
I know this is going to be the whole page here.
That's okay. I mean, my goal here is to have an informal discussion anyway. But essentially, if you remember here, so let's take hydrogen. I put a subscript N. So essentially, you could have, for all atoms, you have infinitely many, but countably infinitely many energies.
Yes.
So, for example, if you burn hydrogen, you can observe essentially each element, when you burn it, has different color. So, let's say neon lights. Why do we see the neon lights have that nice bluish light? That's because you see different energies, light
Okay.
from different energies being emitted.
So you are saying that each atoms can have different states, and the states with the lowest, that ground state is the one that has the lowest energy. Okay, that's
Yes,
fair. Yeah.
100% right. Yeah. Yep. So this is such a difficult problem, actually, what I'm trying to talk about, that this is one of the problems that quantum computers are meant to deal with, simulating a quantum many-body system. And that's actually something that Google tried to show this past August. They used Hartree-Fock approximation to deal with certain small molecules made out of carbon. And right now there are calculations that are able to, they're doing calculations that we're able to do 50 years ago. So in a sense, what I'm trying to say is that maybe there's another way we could push the limits on classical computing that can squeeze a little bit more knowledge using machine learning on this problem without having to implement a quantum computer. And this paper I found recently, which I'm not exactly sure about the details of it, but tries to use deep neural networks to essentially deal with the problem I'm trying to present. Excuse me. So this is an active field of research. I mean, you can see that this paper came recently. Yeah. So you might say, well, we have a hard time simulating atoms, even harder time simulating molecules. How on earth will we be able to simulate any real life material which has nuclei left and right with their protons and their electrons kind of mingled together, like the picture I'm trying to show here? Well, one way to approach this is to start from those microscopic laws of nature through the Schrodinger equation and just use approximations. And sometimes these approximations are strong enough, like let's say with a crystal, which has periodicity, the periodic values help us to solve this problem. That's one approach. Another approach is to just completely ignore the specific details in the microscopic level and try to introduce a toy model to try and encapsulate some basic behavior. And this kind of models is what I'm going to show next. And those tend to be spin models. Probably the paradigm and the simplest model to deal with is the so-called Ising model or Ising model. I'm not sure how you pronounce the name. And that came like 100 years ago. In the picture I'm showing, we have a two-dimensional array. And at each location where black ball is, we could have either a spin up, which is a value of +1, or a spin down, which is -1. And given a location, we only interact with our neighbors, with our nearest neighbors directly. And this is the Hamiltonian governing our system. So one might think, okay, how much knowledge can we get out of this system? But one thing that it's a little bit counterintuitive is that even though spins, let's say at the lowest right corner over here, is not directly connected with a spin almost to the upper left, through the direct connections of the intermediary, essentially they establish some sort of correlation. Now, this problem, the next step, what we do as our next step is to embed this lattice with our spins into an environment with a certain temperature. And by doing that, each configuration M, where M means it's a configuration of the spins at each location, obeys this probability distribution. And the energy here is being calculated by the equation I showed in the previous slide. Here, Z is a normalizing factor, and it's just to keep it being a probability density distribution. And Vita is the inverse temperature, which, as the name implies, is 1 over the temperature up to a constant. And this constant is called the Boltzmann constant, and it's a real positive number. Now, if we have a system which is small, like a 4x4, a matrix that, like the one I showed before, then you have a handful of configuration. But as you increase the system, the number of configurations grows exponentially. So already for an array which is 10 by 10, you have 2 to the 100 configurations. That's a problem, because if you want to find expectation values using this probability distribution, it becomes almost impossible to calculate the normalization constant, since we just have so many configurations. And again, a real life material has 10 to the 23 atoms. So we're talking about a massive number of configurations. Now, some things we want to learn from these systems, from this Eisen model, is the specific heat and the average energy of the system, given a specific temperature Vita. And this is how we find these values. And you can see that the specific heat is related with the variance of the energy. And some results I'm going to show you is you can see that at low temperatures, the average energy tends to be low, whereas at high temperatures, the energy tends to be high. And there's an intermediate stage, which is defined by this red line, which I'm referring to as the critical temperature. So if we look now at the variance of the energy, we notice that as we approach the critical temperature from left and right, the specific heat, or the variance, explodes. Now, it diverges, basically. You cannot really see it in the picture I have here, and that's because sampling becomes tricky around this neighborhood. So that's something that is challenging in physics in general. How do you sample in a computationally efficient way and still get the physical information you need? Now, this is, like, as I have said, one of the simplest models when it comes to spin models. What we are working with is called the spin fermion model, and it's completely different, but it keeps some certain ideas from the previous model. In our case, we're working with an one-dimensional chain, which is represented by these red boxes. And in each side, you have an atom where the nucleus, which is this blue ball, can take classical values for its spin, whereas the electron behaves quantum mechanically. In our system, the only interaction you have is between the electron and the nucleus. However, we allow for the electrons to hop from side to side. And by this hopping mechanism, whatever interaction between this nucleus and this electron happen, by hopping, we essentially indirectly couple neighboring spins. Mathematically, what the spin operator for the electron is becomes the Pauli matrices. And for the nucleus, since it's a classical vector, we just require it to have magnitude of 1, and it can point at any direction on the solid sphere. And that can be parameterized using two angles, theta and phi, the longitude and the azimuth, which take these values. Again, this is our Hamiltonian, which is, I'm just showing it just for completion. But what should become clear here is that this is a matrix. And as we increase the number of nuclei, well, as the number of nuclei goes up, this matrix, the size of it grows exponentially. The quantity that we care to calculate in our project is what we call the free energy, and can be found exactly using this formula. However, since if we have any big enough system, our Hamiltonian becomes extremely long, extremely big, we want to find another way of approximating the free energy without having to perform this calculation here. So our first inclination was to try a linear regression model, where essentially what we did is we create samples where we chose different configuration of the nuclei spin, where they're pointing at different directions. And then we tried to see how they interact with each other. And our model more specifically had a constant offset. And then it coupled these PR terms. These PR terms essentially are families of dot products, essentially, where let's say you have P1, you just sum up the next closest neighbors, the dot product of the next closest neighbors spins. So our goal is to simplify the model and avoid doing all the calculations on the big matrix and try to just concentrate on the input data that we had. So we started with a moderate length chain, L equals 20. And here in this plot, the true energy, using the exact formula I showed before, showed on the x-axis. And our model's energy showed on the y-axis. The red line is the theoretical value, and the blue dots are the predicted values. And as you can see, the model performs extremely well. We wanted to see how well the model could do in a much larger chain. So we repeated the experiment for a chain length of 60 and 100. And we can see that this model seems to encapsulate pretty much a good chunk of the information of our system. Now, having done that, we thought of approaching the problem through a neural network perspective. Oh, sorry, never mind. I apologize for that. So our goal next is to see how these coefficients, see the values of these coefficients. And as you can see, even though we tried 3 different models, pretty much all coefficients seem to overlap for each different R. As you can see again, the lion's share of the contribution to our model goes to the J0 coefficient, with all the others being close to 0. If we zoom in on the rest of the coefficients by without looking at this R equals 0 coefficient, we can see an interesting effect. First of all, we can set for all these three different chains, the coefficient for a given R are pretty much close for the different spin chain lengths. And that's good news, because we could use the information from a short chain and feed and essentially get the same information for a much larger chain. Another interesting thing is that we have this oscillating behavior where all odd number R are positive and all the even number R are negative. And also we have this exponential decay behavior, which in a sense makes sense, because if you remember the model, we had the nuclei being next to each other in a chain. So you will expect the nearest nuclei to have much bigger effect than the further away. Now, as I said before, we tried to use a different approach to this problem using neural networks. And what we tried to do is we had some feed-forward network, in a sense, where the inputs were the components of each spin given its side. Then in our hidden layer, we split the nodes into families, which are denoted by different colors. And each family essentially took the input values from two different locations, add them together, and use an activation function. So for example, the article 1 family the articles 1 family takes a spin from the next nearest neighbors, and all the red cells have the same weights, whereas the R2, the yellow family, takes spins from sides that are separated by 2. So in this case, this guy and this guy. And again, all the yellow cells have the same weights, but the weights of the yellows are different than those of the reds. Once we have all these different cells, we add them all together in each family, and then we add them all together in general. And the output should be the free energy. So our goal again was to train our model in a smaller chain where we can create enough number of reliable samples in a reasonable amount of time, train our model in a small chain, and use that model to feed bigger chains by replicating the hidden layer, essentially. So that's what we did. We try our trained model on short chains, but bigger than the chain we started. So we train our model in a chain of 20 spins, and we use a maximum R of 10. So the furthest away you could go was 10 spins. And then we we use that model to feed much longer chains. And here on the x-axis is the predicted energy, which is reversed than before. And on the y-axis is the true energy. Again, the red line is the theory, and the blue dots is the predicted value. We're doing great job when it comes to short chains, as well as much longer chains. So this is like L equals 160, which is 8 times longer than the training chain. You might notice that we're slightly, we have a slight offset from the true value. And that's something that we've been currently investigating. So having done this work, our goal is to, oh, yeah, sorry, I jumped the gun again. So when we come to see the weights of each given family, we see again the oscillatory behavior, where this time these guys are negative and the odd number are positive. And again, we see this decaying behavior like we saw in the linear regression model. And that's positive. That's reassuring because the two models seem to come to an agreement about the general structure of how the solution should behave. Our next goal is to take this model and extend it to from 1 dimension to 2 and 3 dimensions, which is, yeah, that's currently where we want to take. That's more realistic when it comes to real material. However, there are systems that we can model in 1 dimension, and we can set up physical experiments in 1 dimension. Our main hindrance right now, our main obstacle is how we can effectively, how can we have an efficient way of sampling? Because right now, just creating enough samples for anything, whether it's training or just for all our purposes, essentially, we don't have it. Our sampling technique is time consuming. Now I'm gonna, yeah, this is one paper that came out 3 years ago and pretty much deals with the IZ model I was showing before and a version of the problem I just showed. And in this paper, they use restricted Boltzmann machines to identify the wave function. So my goal here again is to show the active research done in the field. Now I'm gonna shift gears and go from the more theoretical aspect to sorry. I'm gonna go to a different approach, different field in physics, which how do we use machine learning in actual physics experiments? And essentially most physics experiments tend to either produce a lot of data, such as LHC, or they might require a lot of manual labor just to perform them. And such an experiment, a place where machine learning can make can be a huge help is how we can streamline actual experiments. And this is a paper from Oak Ridge National Lab where they use Gaussian processes to make microscopy much faster. Essentially, they had a material and they tried to scan it in an efficient way where they could still get all the information they needed for the given material. And they use some, as they point out in the title, a non-rectangular way of scanning the material. On a different approach, this is a paper from LHC where they built a detector and they wanted to characterize their equipment. And the reason they want to do that is so they can identify the systematic errors as well as the actual behavior of their equipment, of their detector. So they will be able to determine false alarm or some true results. And again, in this paper, they use machine learning to perform that task. Going from the smaller scale to a much larger scale, we have the Deep Skies lab, where they take data from astrophysical observations and they try to go through it to identify galaxies, as well as to give predictions about cosmic microwave background. And these are some of the efforts where machine learning has helped with data analysis and experiment performance in physics. Overall, I have a really positive outlook on how these two fields can marry together. When it comes to quantum chemistry, I think machine learning can be a valuable tool, which will enable us to calculate in a much more efficient way wave functions of a system, and will allow us also to calculate expectation values of different operators. As I have shown before with the Ising model and the spin fermion, we can get insights about models with phase transitions that can be ideally, tend to be universal models and can explain different phenomena. And lastly, I believe that machine learning could definitely streamline data analysis and experimental physics, as well as our understanding of the actual equipment we're using. I would like to thank my supervisors, Pau Glosas and Denis Ardogmush, as well as my coworkers, Thales, Bahar, and Gerald, for all their help. And of course, our collaborators in the physics department for all their help, Adrian, Phil, Doug, and Hongwei. With that, appreciate your attention, and I'm open for questions.
Thank you, Yorgos. Thanks for the nice talk. Anyone has any question for Yorgos about any of the aspects we're discussing today?
So I ask another question, and if you don't mind, let me ask actually a question that my student just posted in a Slack about your work. Would you mind giving us a little bit some insight on the Schrodinger's equation, and what is phi, what is E? I mean, E, you mentioned about the energy.
Let me go back to it.
Great.
Sorry, I'm taking you through this. So like this equation, starting from hydrogen.
Very early equation, yes. I mean, for hydrogen, yeah, just give us some physical implication for different parameters here.
Yeah. So like these parameters here are just all constants. And this is like the charge of the electron, which happens to be the same but opposite for the proton. And this is essentially the second term here, which I have in red. That has to do with this classical picture of an electron being attracted to a positive charge. The most difficult term to explain is this term here, which is essentially having to do with the motion of the electron. Because the electron, essentially, we think about it as going in circles. And that's being encapsulated essentially by this term here. The most challenging thing to explain probably is the wave function, what it means.
Yes, and this was the main question that my student had. Yeah, these are quantum states, and yeah, what does it mean even?
So what you do is that essentially you treat the wave function as a probability density function. and you ask yourself, what's the probability of, if I put a detector of finding an electron at location R, at this angle and at this angle? And that's pretty much how you get it. So you get a probability out of this thing.
But shouldn't they be, quantized? I mean, a specific location, we know that the electron cannot be, and so how do we have the quantum part of that? How do we solve that with the quantum constraint?
So the quantum constraint, the discrete part, is the energies. So would you mind repeating your question, actually?
Yeah,
just to make sure I understood.
Yeah, this probability density that you mentioned, this
Yes.
phi and theta. So are we having a location that electron cannot be, or no? This is
Yes.
So how do we constrain the solution to make sure that we actually discard those solutions?
So a priori, we don't know, but for the hydrogen atom, we know that for any n bigger than 1, for any L bigger than 0, we know that at R equals 0, the wave function goes to 0. So a priori, we don't know where the wave function will be 0. So that's something that we know after the fact, once we solve the equation. So that's kind of the problem with the helium atom. Essentially, you could ask, are there any constraints we have about this wave function? And there's actually a little bit more constraint. Like one of the constraints we have is that if you permute R1 and R2, you pick up a negative sign. So that's the only physical constraint we have. So just to make it a little bit more concrete.
Equal to minus of.
Yeah, that's due to the Pauli exclusion principle. But besides that, we don't have any other.
Thank you.
Yeah.
Any other question for Yorgos? Of course, you can always reach out to him afterwards.
Yeah.
Suggesting some of these topics, some ideas come up. I'm sure Yorgos will be glad to take those later on also.
More than happy. And this is really dense material. Just bear in mind that people spend decades trying to just go from step 1 to step 2. So it's pretty dense. It's nothing too, nothing basic or easy.
Okay, last chance for questions. Then I guess we can conclude this seminar today here. And thank everyone for tuning in and staying here. Thanks, Yorgos.
Thanks, everyone.
Thank you.